I'm Gonçalo, and my presentation is about, I will try to start with a brief overview of optimization and different methods and problems that we can approach in this topic. But then I will try to move, try to start from more tactical environments and then move to more dynamic ones where we have sequential decision making, and also how can we use artificial intelligence and in particularly explainable AI to approach these kinds of problems. So my presentation is divided in these three parts. I will start with introduction to optimization and static environments, and then move to these dynamic settings, and finally talk a bit about explainable AI and a specific technique that we have been exploring to approach these types of problems. So when we look at the different questions that we can try to answer with analytical methods, when we try to study a system, first we try to describe what is happening with that system. And once we are able to describe it with statistics and machine learning, then we can try to predict what might happen with that system with methods like supervised learning and those types of methods and inferential statistics and time series models. And only when we really understand how our system works and what can happen with our system, then we are in the position of defining what should we do. And sometimes defining what should we do is obvious based on the answers to the previous questions. Sometimes it's not. And when it's not, often optimization is really an important tool to be used. So what is optimization? Optimization is a set of techniques that allows us to navigate through different alternative solutions to our problem. And as defined sometimes by the literature, it concerns the allocation of resources among these different solutions, these competing activities, usually respecting a set of constraints that we need to satisfy. So an example would be when we try to define what are the quantities that we are going to produce of a set of products. So let's say we have two products and we want to maximize the value that we obtain from producing those products. So we are trying to maximize this objective function, but as resources are not unlimited, we cannot produce infinity amounts. So we need to respect the availability of our different resources, right? And we might have capacity constraints that relate to the production, to the warehousing, the storage capacity, distribution, and so on. Another example that is a very well-known problem is this transportation problem, where we are trying to optimize the quantities that we are transporting from a set of suppliers to a set of customers, right? So indeed, each of these distribution channels, each channel has a specific cost, and our objective is to minimize the total transportation cost that allows us to fulfill all the demands of our customers using the available capacity that we have with our suppliers, right? So these two examples are examples of what we call linear programming problems, where everything is linear. The objective function, the constraints, the decision variables are continuous. So by applying methods like the simplex method, we can very efficiently, very quickly find, most of the cases, the optimal solution. Things get a bit more complex when we look at combinatorial problems. And not all combinatorial problems are the same, and there are some specific ones that are actually easy to approach, but some other ones, which we call non-polynomial time combinatorial problems, those are really hard. And that's probably the most common one is the traveling salesman problem, which many of you might know, but it just consists of defining the sequence of cities or locations that we need to visit in order to minimize the total distance that we cover. And as you can see, the number of alternatives, the number of solutions grows really, really badly, so it does not scale really well, right? So just because the factorial is sometimes hard to understand by our human minds, and just to make this more explicit and show you that explicit enumeration would not be a feasible approach. When we have 10 cities to optimize, a very fast computer would take a very small fraction of a second. But when we grow this to 25 cities, the same computer will take 1 year to go through all the different solutions. And if we grow this to 32 cities, we would need 3 times the age of the Earth to be able to go through all the solutions. So really, exhaustive search and explicit enumeration is not feasible. So what is feasible? What is feasible, and how can we approach these combinatorial problems? By methods like the branch and bound, which does not explicitly enumerate the solutions, but somehow implicitly enumerates the different solutions. Because we can know that some of the solutions are infeasible, do not satisfy our constraints, and some of them are dominated by solutions that we find in the middle of the process. So by identifying these solutions, we are able to cut whole regions of the solution space and allow us to really, if we invest enough time, to reach the optimal solution without going explicitly through all the different solutions. Okay. One other approach is constraint programming, which is also an exact method, allows also to find the optimal solution, but in this case is by propagating constraints on the solution space and try to reduce the solution space as much as possible, preferably to a couple of solutions that we then might enumerate. And specifically this method would be very, very interesting for problems that are very constrained. So think about timetable scheduling, where we need to make sure that we don't have one speaker at the same time in multiple rooms, or the same people, or in the same room we don't have overlap of sessions. So when we have a lot of constraints and a lot of unfeasible solutions, this would be an interesting approach. And so again, if we invest enough time, we are able to also to find the optimal solution. When that's not feasible, when even using these more intelligent methods is not feasible to in due time find good solutions, then we can use approximate optimization methods like heuristics and meta-heuristics, right? So picking on the traveling salesman problem, this would be a very well-known heuristic would be to apply the nearest neighbor. So start iteratively by the nearest neighbor and then go on with this procedure until we have a complete solution, right? And then this solution seems reasonable, but it might not be optimal. So we might even try to improve it iteratively by, for instance, selecting 2 of the arcs of this graph and rearranging the graph a little bit to try to get an improved solution. So if we do this iteratively, we might, after some time, arrive at a good solution. And sometimes we might be trapped in local optima, and there's different alternatives and different ways of escaping that local optima, and that's what meta-heuristics are all about, right? Both neighborhood-based meta-heuristics and population-based meta-heuristics. So, an example of a problem that we have approached with these methods, in this case, it was a scheduling problem with collaborative robots. And in this case, we have to make 2 main decisions. First is, we have a set of jobs to be executed, and we need to decide each job by what resource is going to be executed, by a human, by a robot, or by a combination, by a human-robot team. And then, for each resource, we need to optimize the sequence of those jobs on that resource, right? So we have these 2 main decisions, allocation and sequencing. So both of them are combinatorial, and we need efficient solution methods. In this case, we have tried all the three classes that I've showed you before: branch and bound, constraint programming, and meta-heuristics. In this case, it was a genetic algorithm. And in our case, constraint programming and genetic algorithms were the most competitive ones, and they were able to find, in our instances at least, solutions that had an optimality gap of 1%, of less than 1%. And then, based on those methods, we were able to solve a lot of different instances and generate managerial insights of what would be the additional benefit, in this case, of having a collaborative robot in our factory. Okay? Okay, so when we look at different optimization problems, it all starts with linear programming. Those are usually the easiest to approach. But then a lot of different things can make these problems more complex. One is combinatorial decisions, as I've shown you, but there are also nonlinear problems that we find usually when we want to optimize machine learning models. And in this case, we would need methods like gradient descent. Uncertainty in our parameters, and we need in that case to use stochastic programming, robust optimization, fuzzy logic. And in some cases, we have uncertainty, and that uncertainty is revealed along the time. And also along the time, we can make decisions. So we have this sequential decision-making setting. And in that case, it all starts with dynamic programming, but usually dynamic programming also does not scale very well. So we need more approximate methods to approach these kinds of problems, things like reinforcement learning, hyperheuristics, and so on. So an example, imagine also a scheduling problem where we have one machine or a set of machines, and we need to optimize the sequence of jobs that are going to be performed on that machine, right? But as soon as the machine finishes a job, 3 new jobs arrive, and we need to re-optimize the sequence of jobs. So in this case, going for optimizing using branch and bound or even a meta heuristic might take too long to solve when we need solutions instantly almost, right? So in that case, what people use in this specific case are what we can call dispatching rules, right? So let's use a very simple rule that calculates something for each job, and then we are able to sort them very quickly. So imagine that we want to start by the shortest processing time, and then go to the second one and third one, and we finish with the longest one, okay? Or we can make this more complex, and instead of looking at a single variable, we are going to look at 2 variables, not only the processing time, but also the queue that this job might find in the next machine that it needs to visit. So considering the 2 variables, it might be better than a single one. So we can then make these dispatching rules more or less complex to approach our problems. And that's what the literature has done. We can even try to automate the generation of these dispatching rules. And this is what methods like genetic programming allows us to do. So genetic programming, maybe a lot of you know genetic algorithms, and maybe not so many know what genetic programming is. Genetic programming is an extension of genetic algorithms that work on the same principles of evolving a population of solutions, but in this case, one solution is a mathematical expression. So as you can see in this example, this expression here is represented by this tree because it is a division between the multiplication and z, and the multiplication is between 2 and the subtraction of x and y, right? So we can represent any mathematical expression with a tree like that, and then we can try to generate better and better expressions by selecting 2 promising expressions and try to recombine them in order to find even better expressions. So we can apply operators like this crossover, or we can even apply mutation operators like this one, where we take a subtree and we replace it by a new subtree. So people in the literature have followed these 2 ways, right? The human reasoning way, where we are trying to manually create these dispatching rules, and those are a bit more complex than just looking at just 2 variables. And there are people also that try to apply AI, and in this case, genetic programming, to generate more complex expressions. The problem is that sometimes it's hard to trust this mathematical expression because it becomes too long and too complex for our human minds to trust, and trust that it will generalize and it will perform well under all circumstances. Still, it's better than a neural network, right? We would never try to really explain what a neural network does. We might run explanators on top of that, but explaining a neural network by itself is much harder. Okay, so what we've done was try to combine more or less the 2 approaches, try to combine human reasoning with artificial intelligence, with genetic programming in this case. So we tried to look at these mathematical expressions that were created by humans, try to see what are the important variables, what are the important operators, if there is a structure that is already there, then that we can start from, and then somehow guide the machine learning process to learn the expression from the ingredients that we provided, okay? So by combining these two approaches, we were able to find a dispatching rule that is represented there that is much simpler than the one that I showed you in the previous slide, and it was able to outperform the state-of-the-art, which was something that was not done since the 90s for this case, for this classical job shop scaling problem. So whenever you see a value here in this table below 1, it means that we are outperforming the state-of-the-art, okay? So it was also good to see that it was able to generalize well because it was trained in the subset of the class of instances that we then used to evaluate the methods. So we applied this to the classical job shop, to the flexible job shop. In this case, the expression was also shorter and explainable, and we were able to even get a relative improvement that was higher than in the previous case, because maybe in this case the problem was not as competitive as the other one. But we can actually apply this to many other dynamic problems. So many problems need these scoring functions. So in this case, we have an online fulfillment problem where we have a marketplace and we need to decide for each online order that arrives at our website, we need to decide what is the stock point that is going to fulfill that order, okay? So in this case, we need a scoring function that is going to run and calculate a score for each stock point and sort them and choose the most promising stock point to satisfy that order. And whenever we make that decision, we might be, or not, compromising future decisions because we are making that allocation, we are depleting the stock in that point that could be useful for a future order that we don't know if it will come or not. So this dynamic problem is not really easy, and learning these scoring functions, we need really to be able to simulate the execution of these rules to understand whether they are effective in looking ahead, in considering future information, and in improving and really optimizing our problem. So in this case, the relative improvement was not very high because also the number of alternatives was not high, but in total the benefit was quite positive. Okay, but not only combinatorial decisions can be computed here, we can also use and learn mathematical expressions to compute continuous decisions. So that's the case of these inventory management problems, where we need to decide whenever our stock reaches a reorder point, we need to decide how many units are we going to reorder to replenish our stock. And if the problem is very simple and demand is deterministic and we have a very simple problem, we already know what's the optimal policy, we already know how to calculate the optimal quantity and the optimal reorder point. But as soon as things become more complex and we have uncertainty demands and so on, then we know, most of the cases, we don't know the optimal solution anymore. So we can use, again, these types of methods to learn these mathematical expressions. But the first time that we apply it, it's very common to really arrive at these very complex and very long expressions. But by performing this human reasoning and this guided search, we were able, and by looking also at the expressions that we could find in the literature created manually by researchers, we were able to find much shorter expressions that are more explainable, shorter, and they were even more performant than those more complex ones. Okay. So that leads us to start and lead this European project on explainable AI, and really the objective is to create this platform, this tool that allows us to promote this human-guided approach that uses genetic programming as the underlying algorithm. So our objective is, so we have partners that are specialists in genetic programming, some other partners that are specialists in user interfaces, in explanations, and in cognition models. So we try to put this all together to generate this tool, and while exploring real use cases in different sectors and some optimization problems, but also some predictive problems. Okay. So the tool is, as we tried it to be as modular as possible. So whenever we want to replace library A by library B, that's something that we try to provide. And also user interfaces that allows us to follow what's happening with the learning procedure, also look at the model, try to manually edit the model, try to improve it manually, and rerun it again. Okay, so at the same time, our partners are trying to improve the algorithms themselves, to find shorter expressions, to work with multi-objective problems, to work with constants inside the expressions, learning constants more efficiently. And to finish, because my time is ending, we also try to promote a multi-model approach where we are trying to learn not just one model at the same time, but multiple models that might be complementary to each other. Okay, so to sum things up, we have, for many prescriptive problems, we need optimization methods. Things can be more or less complex depending on whether we have combinatorial decisions and certain parameters, nonlinear equations. But as soon as we have a dynamic problem, then we need a whole new set of optimization algorithms, and even machine learning can be important here. So I personally believe that genetic programming is an underutilized tool in this context because it's really powerful to promote this human-guided approach. So, but we know, of course, that a lot of developments are still needed, both on the algorithms and on the interfaces with those algorithms. So that's all from my side. Thank you very much.
I think Gonçalo, we still have a couple of minutes for some questions, and I will remember the audience if you want to drop some questions to our speakers. So let's start for the first one. When it comes to defining an evaluation function to real-world problems, what is the rationale to use? And actually, I want to add in something that is optimization is something that is concerning different subjects in different fields. How we can select the best algorithms to actually optimization algorithms to our problems.
That's a very open question, and it's hard for me to answer such an open question, but I'll try to provide an overview of what are the things that we should consider. Those include whether our problem is linear or non-linear, whether it is combinatorial or not, whether we have uncertainty, whether we have dynamism. And based on that, I believe that we can already go to a family of algorithms, but then it really depends on further characteristics, like do we have a large solution space, a very small solution space? Do we have, I don't know, do we have a multi-objective problem? Do we have multiple local optima? In that case, exploration is really important when we apply a meta-heuristic, or do we have really complex solution space to navigate, and in that case maybe a neighborhood-based meta-heuristic might be better. So a lot of different characteristics that are at play, and it's
okay. Let's just try to pick another one. To find similar or same functions from the literature as the output of the GP algorithm, did you use any tools, or did your team just know them?
To develop what?
Is the similar same functions? Actually, I'm not an expert on the topic, so I'm a little bit out of fit here. But
to find similar functions from the literature. So I don't know if the question is asking about how do we find the expressions, what libraries have we used, or how we consider the existing rules from the literature in our search.
Yeah.
So I will try to answer both. So in terms of libraries, we have used different libraries. We are also working with our partners that are developing these more efficient GP algorithms that converge naturally to shorter expressions. So, then I can list different tools, but we have used, for instance, ECJ, which is an evolutionary library that is able to approach both genetic algorithms and genetic programming. We are working with our partners that are developing GP GOMEA, MESGP, mimetic semantic GP. So those methods are really, some of them really the state of the art in terms of this trade-off between performance and explainability. In terms of the expressions that from the literature, sometimes we use them as starting points, really, in the initial population that GP is going to use to evolve and to try to find better expressions. But most of the times, even without using them as starting points, GP was able to either find them or outperforming them. And that's based on the effectiveness of the algorithm, but also on the guide that we try to provide to GP, understanding really what are the variables that are important, the operators that it needs to achieve something similar or better than the expressions that the literature has found.